Okay, so here we go. We're going to talk about function composition. Function composition a little bit different than the last couple of days. The last couple of days we did addition of functions, we did subtraction, multiplication, and division, where basically if you want to find the y values of the sum of two functions, you just take the y values of the individual functions and add them together. Same goes for, subtraction, multiplication, and division. So this one's a little bit different because what we do with function composition is we basically take the output of one function and use it as input for another function. And we can think of that very graphically. This is a diagram that I use. I'm sure I know that Mr. It's just a circle. That's the notation. We're going to get there. We're going to get there. Yeah. I will, I promise. If you think of a function as a black box where you put an f in, and you put an x in, and if this is the function f, out comes the result, and we call that f at x. So this is a diagram that certainly I use, and I know Mr. Falls uses when he talks about functions. If we then take that output and plug it into the function g, our output then becomes, in this case, it would be g at f at x, because we evaluated the function g at the value of f at x. And we're going to do an example so you can see how this all works. So this is the idea of function composition. We've composed two functions. We've used one function as the input, the result of one function as the input for another function. So the notation looks kind of funny. There is this little circle. I forget what the circle's called now, but hopefully it comes to me. This f with the little circle here, g, means that f is composed of g at x. And the other way that you would write this is that this is just equivalent to f at g at x. So we're going to substitute x into g, and the result that we get is going to go in as the input for f, and then we're going to get the result. That's exactly right. Yeah. John?
No, it's written two different ways. The f in front there and g in front there, but they both mean the exact same.
Actually, no, they don't mean the same.
Why would you use the f first?
Well, because I guess I started with f here. Here, I'll fix it. You mean right here? Yeah. Sure, let's do that. Then it would match. So let's put g here, and we'll put f over here. This is g of x, and then this is f at g of x. Is that better?
Yeah.
Okay. I thought about that as I was putting that up. So John brought up a good point about how before it was backwards. If we do it backwards, we're not going to necessarily get the same result. So we could actually say that g composed of f at x is actually equal to g at f at x. Sometimes I call this lesson the fog off lesson because we've got the fog and the goff. So we call it the, yeah. This is my excuse to see who's paying attention. So let's have a look at an example. We can do this a couple of different ways. So I might do the first example a couple of ways, but after that we'll probably just take the shorter route. So if we have two functions, f of x, which is the square root of x, and g of x, which is x squared plus 9, and we want to find f at g at 4, sorry, f composed of g at 4. And I'm just going to move this a little bit. Oh, I was afraid that was going to happen. Never mind. We could actually take this. Remember that this just means f at g at 4. So the long way to do this, and I don't know if it's really much longer, but the long way would be to evaluate g at 4. So we could say, okay, well, what's g at 4? Plug a 4 in here. that okay?
No.
Did I do that wrong?
Yeah.
Really? Oh, it's possible. So we just found that G at 4 was 25. So then we can use that 25 as the input to F. So then F at 25 is equal, is equal to the square root of 25. I didn't have quite enough room, which is plus or minus 5. Yeah. So that's kind of the long way. When I say it's long, it's not really. I mean, you can see that we didn't take a lot of time to do that. I'm going to just tidy this up a little bit so that now that I've moved things, we can fit things a little bit nicer. So the other way that we could do this is to just kind of combine these two steps into one and say, okay, we need to take 4. Oh, this is kind of, no, I don't think I can anymore. I think this thing just like this, like the other way. Sorry. Is that better? Or is that too far? Too far. Okay. So F at G at 4 is, I'm going to go up a little bit further just so I can see the functions. We need to take G and evaluate it at 4. So G is, I'm going to leave a little bit of space here because we're going to need it. 4 squared plus 9. And then we need to evaluate F on this. Well, F just means we're going to take the square root of X. Well, here's where we're going to take the square root. The result is exactly the same. We're going to get the square root of 25, which gives us plus or minus 5. And John had asked earlier whether G composed of F with F or F composed with G were the same. Here's an opportunity to see whether that's true or not. Maybe take a minute and see if you can evaluate F composed, G composed of F at 4. So I'll give you a minute or so to do that. Yeah, John? Yeah. Well, because remember, this says to take F evaluated at G at 4. Well, we just figured out that G at 4 was 25, so now we want to find F at 25, so we plug that in for F. No, that's a valid question. That's really the whole basis for this section. So if you can understand that, then you should be okay. Try the next one and see what you get. So G composed with F, that's the same as G at F of 4. So in this case, we can find F at 4. So that's the square root of 4. But then we plug that into G. Everywhere we see an X, we're going to plug in a square root of 4. Yeah, square root of 4 squared is just 4. We add 9, and we get 13. And you can see the answers are different here, which is fine. We sort of talked about that already. Really important that you understand that the function composition is not an operation or an operation that is equal forwards and backwards. Is that okay so far? Some very concrete examples there where we actually plugged values into each of the functions and got an answer. Part C asks us to find an actual expression or a function, and if we can find a function because it's going to operate on x, then we could have actually, we can sub in, hundreds of values if we want without having to go through all of the operations. So that's kind of the point of part C, is that let's actually write one function now that represents the function of f composed with g. So to do that, we're going to substitute an x into g. Well, that's already done for us. So that's x squared plus 9. But then we have to take the square root of that because we need to compose with f. So this becomes the input for f, and we get the square root of x squared plus 9. I should have maybe just, as a reminder, written this down. We wrote it down on the other two. I probably should have been consistent here. We want to evaluate f at g of x. No. You want to split it apart, you mean? And take the square root of x squared and the square root of 9? No.
Because the f's in the front. It applies to everything in brackets.
Right. But I think what Jen was asking was, can we just split this apart? If we just had this, forget everything else. If we just had the square root of x squared plus 9, we can't just split that apart to the square root of x squared plus the square root of 9. But you could if they were multiplied, right? If it was 9x squared, then you can pull it apart. Yeah. So that's just rules of square roots or radicals that you talked about in grade 11. And just probably worth noting here that generally speaking, f composed with g at x is not the same as g composed with f at x. What's that? Oh, thank you. Change this to a G and change this to an F. Yep. Yep. Nope. Nope. Not the same thing. Leslie? Yeah, you could, I suppose. Yeah. Definitely, function composition doesn't necessarily, just like with function addition, we could add 3 or 4 or even 5 different functions together. I don't think you saw any like that in the work that you did. You may have seen 3 at the most, but the point here is to give you an introduction to these ways of combining functions. Once you understand how to do 2 functions, 3 functions is the same. The result gets a lot messier, or could get a lot messier, but the process is the same. I'm starting to warm up. Hands are freezing still. Any questions with that so far? I don't think there's much else. Oh, never mind. There's 3 more pages. Yeah, sorry, I forgot. All right, here we go. Example number 2. Now that you know how to do this, why don't you give this a shot? So f at x is a quadratic function equal to 2x squared minus x. G of x is a linear function equal to 4x plus 1. And typically when I see these functions written in this notation, I always kind of think that, hey, yeah, this just means f at g of x. So that means you're going to substitute g into f everywhere you see an x. And it's everywhere that you see an x. Just like when we were doing the rates of change at the beginning of the semester, we talked about how you did an x plus h, you substitute an x plus h into the function. Everywhere you see an x, you replace it with an x plus h. And in this case, everywhere we see an x, we're going to replace it with this function here, g of x. Yeah, expand and simplify when you can. You're not always going to be able to do much simplifying, but if you can, in this case, you should be able to do some. If you can, make sure you do it. So again, we're going to take g of x, and we're going to substitute it into f everywhere we see an x. So it's going to go into that x, and it's going to go into this x here. So we're going to get a result of 2 times 4x plus 1 squared minus 4x plus 1. And again, let's expand, collect like terms, simplify. One quick thing here, I just noticed that I didn't do. Make sure you put some brackets around here because we're subtracting the whole thing. We're subtracting all of x, or in this case, all of g of x. So put some brackets around there. So I just expanded 4x plus 1 squared. 4x plus 1 times 4x plus 1 gives us this. Multiply the 2 through the brackets. And then simplify. Did I do that right? I'm going to guess those of you that messed up on the expanding of the binomial. Is that right? Yeah, it's a common mistake. The 8x came from doing 4x plus 1 times 4x plus 1. So the 4x comes here, and it also comes here. Remember the shortcut when I talked about this early in the semester. The shortcut when you expand a binomial is to square the first term, which I did. 4x squared gives us 16x squared. We double the product of the first of the two terms. So the product here, 4x times 1 is 4, times 2 gives us 8x, and then we square the last term. It's probably a good thing to kind of get used to because obviously squaring binomials happens quite a bit. In the polynomials unit. And I mentioned it when I always say that, hey, if you took data management and you did the binomial theorem, this is a good application of the binomial theorem because this is exactly what that's all about. Pascal's triangle. Yeah. Mathematician, famous mathematician. There's also a computer programming language named after him. Let's go the other way, and let's try g composed with f at x. So that means we're going to substitute the function f into all of the x values in g. So for this one, everywhere we see an x in our function g, we're going to substitute that value in right there. So this will equal 4 times 2x squared minus x plus 1. Expand, collect like terms, and you're finished. 8, I guess there won't be any like terms. Yeah, that's a common pitfall number 2. So in this case, we've got 2 quadratic functions by doing the function composition here. Obviously, they're different. And I wanted to show you this one for a couple reasons. Tricks, not tricks, but things like this where you have to subtract and obviously the squaring of the binomial, or it could be cubing or whatever. Any questions on that one? Is everybody done? Anybody not done? Yeah, so now let's get into some that are a little more complicated. So far, things kind of worked out fairly nicely. We ended up with a couple of quadratics at the end. Let's try it with some functions that, I mean, not that log is ridiculously messy, but it's one that you're just getting used to, right? Yeah, you would, yeah. So I'll give you a minute to try that out on your own, see how far you get. Not see how far you get. See if you get it finished.
Just ask the question.
Well, I'm not going to tell you the answer. Not yet, anyway. Here's another way. I probably could have written it this way before. I didn't, but if you wanted to, you know, some of you like to have things broken down step by step, neatly organized. G of x is just x plus 4, so we want to substitute an x plus 4 into f, so you could write it like this. I think some of you might want that. And then you can just substitute everywhere you see an x in f, you're going to replace it with an x plus 4. So we're going to get the log of x plus 4 base 2. So yes, Aaron, you are correct. There's nothing we can do here to simplify this. It might be worth putting this in brackets. We probably should, just so that you don't think it's the log of x shifted up 4. So we're taking the log of that whole x plus 4. Questions? All right, so now we get to an interesting scenario here. We haven't talked about domain yet. For all of the functions that we've looked at so far, with the exception of division, the domain was just the intersection of those of the domains. In this case, it's not necessarily the intersection of those domains. We have to kind of look at what we're left with. In this case, we're left with the log of x plus 4 base 2. So let's look at a graph of the log of x plus 4. So here's the log of x. Base 2. What's the plus 4 going to do to the graph? Yeah, it'll shift it which way? Shift it left. So where are we going to end up? Somewhere over here, right? We're at 1 here. We subtract 4. We'll be over here. So we get this happening.
No, it'll be 1.
Yeah, it should always, well, it'll be 1, yeah. I don't want to say always 1, because obviously we just shifted it and it's not 1. But
How do you know log base 2 is different than log base 2?
That's a good question. How is 2 to the x different from 10 to the x? Does that answer your question? Awesome. Yeah. What's the domain of this green function that I just put on the board?
That's the adjective.
Negative. I heard a 4 and a 5. Any 3s? Hey.
Hey, you have Jesus right where I pick one.
Sure do.
I'm gonna look him up. So he has this period. I can't have access to 0.
Oh, yeah.
It's one of my kids' binders.
He has. Isn't he with you?
No, that's period 4.
Oh, yeah. Yeah, just give me a second. No, that's okay. Oh yeah, this function right here, the domain. Whoa, I heard a -4, a -5, and a -4.5.
It's not -5.
Oh. Yeah, the asymptote was 0 before. We shifted 4 to the left. So the asymptote is at -4. So the domain of this new function then is that x is an element of the reals such that x has to be greater than -4. What about the range?
I have a question.
Yeah, sorry.
Dumb question, but element of the reals, why do we put that if it's going to be any number? Because when is it not going to be an element of the reals?
Yeah.
We haven't fallen, they come graph yet.
There was a question in the homework 2 days ago where you had a set of ordered pairs. Function f was one set, a whole bunch of ordered pairs, and function g was a different set of ordered pairs. In that case, x wasn't an element of the reals. X was the x values. There was a 1, a 2, a 3, a 4, and a 5, I think. So in that case, x wasn't an element of the reals. X couldn't be any number. X could only be the numbers that were listed there. The other time, and we don't talk about it much in math, but the other time where you might have a function that's not an element of the reals is, let's say we're graphing the number of people who attended, some number of people in a doctor's office, say, over the course of the day. I don't know. Right, so you can't have 0.5 of a person, right? So in that case, your graph isn't... Or what if a person lost their arm and their leg? Is that like 3/4? No, but we count that as one person, right? So in that case, if the function were linear, where at the beginning of the day there's hardly anybody there and it kind of grows and stops, so then x can't be an element of the reals. In that case, x would be, I was going to say an element of the integers, but they can't be negative either, right? So they have to be an element of the either the natural numbers or the whole numbers. So the natural numbers would be like 1, 2, 3, and so on. So you know how we do the x an element of the reals? If you want to do x is an element of the integers, in high school I think we say that x is an element of the integers we say is an I. Technically, like when you go to university, it's going to be a z. Hey, look outside, you can't see anything.
That's what we're looking at.
Oh, yeah, this is great. I love the day at school.
I'm glad I just distracted everybody. The natural numbers would look like that, and the whole numbers would look like this. So the natural numbers are like 1, 2, like the normal counting numbers, 1, 2, 3. The whole numbers would include 0, 0, 1, 2, 3, and so on. Negative numbers and positive numbers. Okay, guys, quiet, please. Right. Yeah. That's right. So you look at the result, which was here, and you say, okay, what does this function look like? Right. Exactly the same. What about the, we didn't talk about it, what about the range of this? Right, so y can just be an element of the reals. We weren't asked to find the range, but that's what it looks like. Is that okay?
Sure.
I think there's one more.
No.
She's right there. So in this example here, we're going to show that if f of x is 1 over x, then f composed with f inverse of x is equal to the inverse composed with the function at x. They've done it. They have canceled the buses on the way home before, and you guys were stuck. Not you guys, but students were stuck at the school until, I don't know, 5 o'clock or something.
Why is
That just means the inverse of f.
so x?
That's a reciprocal. So remember that an inverse function involves switching x and y and then solving for y. So it's probably worth spending some time, not probably worth, we need to find the inverse of this. So in order to do that, here's the function. We're going to switch x and y. Yep.
So isn't it just going to be y equals?
So then you solve for
Yep.
y stuff?
We're going to solve for y. So we want to solve for y. We want to get y on one side of the equation all by itself. As Leslie said, hey, let's multiply both sides by y. And then solve for x. Divide both sides by x, and we get y is equal to 1 over x. It's not always the case, by the way, that you just get the switching of positions, right? If I had a plus 5 somewhere in the equation, that would change the equation. But I wanted to keep this fairly straightforward because I didn't want to lose.
So the inverse is the exact same.
In this case, it is, yeah.
Just in this case, so.
Yeah, not always, though.
Okay.
Yeah, in fact, if I throw in one extra number in here, if I throw in a number like this, suddenly the inverse is not the same because this becomes an x minus 5,
Okay.
right, when we subtract and so on. Anyway, I'll get rid of that. So remember, to find an inverse, swap x and y, solve for y. So this right now is the inverse function. And now we can calculate, determine what f composed with its inverse looks like.
Oh, okay.
Why is it
So 1 over
So 1 over
1
x.
over x.
Yeah.
Yeah.
You flip it so it's 1
Yeah.
x over 1, right?
wait.
Sorry, there's a lot of questions. I'm glad you guys have questions, but let's just try one at a time. Did you have a question, Tony?
Why is that negative 1?
That's just how the notation, that's what it is. Whenever you have a function with a negative 1, that's an indication that it's the inverse function.
Oh, maybe, yeah.
Right. Yeah. Because it's a function, like f is a function, not a number. So it's not just an exponent. It's like when you had sine to the minus 1 when you do trigonometry. When you have that on your calculator, it looks like it's the sine to the minus 1, but it's actually the inverse sign. Perhaps one of the problems with mathematics notation is that there's two things. Well, I don't know. Let's have a look. So this means that we have to evaluate f at its inverse. Well, we already know that the inverse is 1 over x. And now if we want to evaluate f at its inverse, we're going to sub 1 over x into the function everywhere we had an x. So this becomes 1 over, I'll do this in a different color even, just to remind you. Looks a little messy. We're dividing by a fraction. What's the rule for dividing by a fraction? Multiply by the reciprocal. The reciprocal of 1 over x is x over 1, so we get 1 times x over 1, which is just equal to x.
So the reciprocal is
So you could just left the asset.
Say that again?
reciprocal is this one?
Yes. Yeah. So we've just figured out what the f composed with its inverse looks like. Now let's go the other way and let's look at what f inverse composed with f looks like.
So they're equal.
They are equal? You've already done it?
No.
Good call.
That's right.
Oh, it says to show that they are equal.
Well, there's the rest.
So we found the one part. Now let's find the other part. We'll talk about why they're equal in just a minute, but let's just quickly kind of get through this. Sorry, I forgot a step. So we want to evaluate the inverse at f of x. F of x is just 1 over x. So we're going to sub 1 over x into the inverse. You did. Before I showed you any of this, would you have guessed that the inverse composed with its function in this case is equal to x? Some of you said of course, some of you said probably not. What if I change the function from 1 over x to, let's say we decided to get rid of this and change the function so it looked like that? What do you think the results might look? How might that change our final result? We did get that the left side here was equal to the right side. Do you think that would still be true if we changed the function here? Probably not?
I think it might.
Okay.
Actually, probably.
Okay.
X squared, but then x squared is x.
Right. And I think you said reciprocal when you meant to say inverse, right?
That's yeah.
Yeah. So if we take this function here, if we say that f is the square root function, the inverse of the square root function is x squared. If we take x squared and apply it to the square root of x, what should we end up with?
Square root of
X. And it's always true that when you take a function and compose it with its inverse, you're always going to get x. I should probably add that in here. I didn't have it in here. But.
Even if the inverse and the inverse are.
That's gonna be on that.
Say that again, Jenna?
Well, like this one didn't this thing work just because the
Yeah.
inverse was the same as the other one?
But the square root one works too, right?
Okay, so it's just the square root, not just.
You just said all.
It's true
You
for...
said not all functions are going to equal.
They're not all going to equal, not all functions will be equal to their inverses, but it is true that every function evaluated at its inverse will always give you whatever your
But
x in this case.
what about every inverse evaluated function? What about this?
Yeah, same thing, because we just found that we got the same thing here, and the same thing would be true here, because the function and the inverse function undo each other, so you're just left with the thing that's being operated on. And that was one of the test questions that you had on the last test, the logs test, where it was, I don't know, 10 to the log 19 base 10 or something. The exponential function here with the 10 and the logarithmic function here are inverse functions, so they undo each other, giving you just 19. Anytime you take a function and its inverse, you apply them to x or anything else, the two functions undo each other and just leave you with whatever the input was. Excellent. That's it for today. There's the homework. I think I wrote it differently on the board there. I decided to take some out for you. Yeah.
Inverse. Then why is it rearranged?
So this is the function. This is f, right? And then we want to calculate the inverse. So we write it with y equals 1 over x. We swap the x and the y values, and then we solve for y, which is what we did here. It just so happens that the inverse is also equal to the original function.